This video is going to look at a special type of ether known as an epoxide. Epoxides are three-membered rings containing an oxygen. For nomenclature, it's actually very simple. It's always going to be the substituent name epoxy, and you will number the carbons of where the oxygen is connected to. So here you have a 4-carbon chain with the oxygen connected to carbons 1 and 2, so 1,2-epoxybutane. Here, still 4 carbons, it's connected to the second and third carbons, pretty straightforward here again, so it's always going to be the epoxide part that's letting you know you have an epoxide. If you have other carbons on that group, you would name them the same way, so here your longest carbon chain would be a 3-carbon chain. Your oxygen is connected to carbons 1 and 2, and you have a 1,2-epoxy 2-methylpropane. You don't need to know this reaction, but now that we're starting to talk about a lot more functional groups, I think it's important. You can see how these things start to occur. You can take an alkene and what's known as a peroxy acid. Notice this looks very much like a carboxylic acid, but instead of having an OH group, it has an OOH group. One of those oxygen actually is going to be added to the alkene, giving you an epoxide and a carboxylic acid. Looking at these relative to our standard ethers we talked about in the last video, you should be saying one of these is going to be more reactive than the other. We talked about ring strain earlier in the course, and ring strain is going to make epoxides much more reactive, and you can see your delta G is going to be a much smaller value from where your reactants are starting with. So epoxides, due to ring strain, are going to be much more reactive. They can be easily opened in one of two ways, and we're going to talk about both. If you use acid, your first step, just like we saw with our other protonation of ethers and alcohols, your oxygen is going to go out and grab a hydrogen, kick off your eventual nucleophile. At this point, you have a protonated oxygen and you have a backside, meaning SN2 attack at that primary carbon. Notice here they're the same, meaning at the end of your product you would have an alcohol on one end and a bromine on the other. This will happen even with core nucleophiles. So again, if we add a hydrogen to our oxygen, we can have a positively charged oxygen. Notice again our arrows, this is still an SN2 mechanism, meaning our OH can come in, break the ring. Our last step here, as always, if we have a neutral nucleophile, it's going to be protonated after we add it. So your last step would be making sure your final product is neutral. So here you would have an alcohol on one carbon that was attached to the epoxide and an ether on the other carbon. So when there's acid around, the nucleophile will always attack the more substituted carbon. So if we look at our sample here, what carbon's more substituted, carbon 2 or carbon 3? Carbon 2 is going to be more substituted, so the nucleophile is going to attack at that position. So here you have your major product being your methanol adding at the more substituted carbon, carbon 2, and your alcohol being on your less substituted carbon. Your minor product, which you wouldn't even need to predict if you saw this reaction on a quiz or on homework, you would see the difference here. Our OCH3, our ether, would be on our less substituted position, and our OH is on the more substituted position. So again, minor product when you're operating under acidic conditions. Why is this the case? The more substituted carbon is going to make the better carbocation. Remember that that oxygen right now is currently having 3 bonds, making it very easy to break one of those. We don't want to say carbocation completely here. It's carbocation-like because, as you saw our arrows on the last slide, we're drawing via an SN2 mechanism. So since it's not a full carbocation, we're going to call it a carbocation-like, and that's why I have it in quotations. So we're eventually going to have that partially positive carbon, and it's going to be a better carbocation-like species than our primary position. So think of it as one of those bonds has to break, which one's it going to be? It's going to result in making the more stable carbocation. Before it can get there, our nucleophile comes in and forces that bond to break. So under acidic conditions, your nucleophile will always be at the more substituted position. Your alcohol will always end up at the less substituted position. We talked about undergoing two different types of products. So if we know that our nucleophile is going to be at the more substituted for acidic, it's going to be the reverse under basic conditions. Here we can see that it's SN2. It wants to be very quick. It's going to attack at the less substituted position as quickly as possible. So here we have our nucleophile coming in, pushing the negative charge onto the oxygen from our epoxide ring. And then this step, either from a solvent or from any acid you want to add, this will then pick up the hydrogen here. So under basic conditions, your nucleophile is going to attack at the less substituted position, meaning your alcohol will end up being at your more substituted position. You can remember both of these acidic and basic conditions thinking about where your OH will be or where your nucleophile will be. So under acidic conditions, you're looking at the more substituted position. Under basic conditions, you're looking at the less substituted position. Don't be afraid that if you see any reagents we haven't talked about yet or haven't talked a lot about yet, if you see a negative charge or a lone pair, you should associate those as being basic conditions. So here we have a basic conditions or a strong nucleophile, which is going to add to the less substituted position. You'll usually see some type of reagent as the second step, adding the hydrogen to your oxygen that was in your epoxide ring. Only thing again here we have a methylamine. Nitrogen has that lone pair. It can act as a nucleophile on its own. So again, it's going to favor going to the less substituted position. Here you might not even need a proton source because we have a positively charged nitrogen and a negatively charged oxygen. It might even take that hydrogen. So you can start to see that our functional groups can get very different very quickly using epoxide rings depending on what your nucleophile is. But the big key to take away here are the differences between acidic and basic conditions and where they will attack on an epoxide.